Today we are going to study the chapter kinetic theory of gases. Kinetic theory of gases. At first, we should know what is the nature of molecules according to this kinetic theory. If you imagine this is a chamber, that is room, which consists of air molecules. So here air molecules are there, but this room is not at temperature which is called minus 273 degrees Celsius. It is at room temperature, far more than this. So since it is at room temperature, every molecule, air molecule, might have got thermal energy by which every molecule will be in motion state because of its thermal energy. As the whole room or system of air molecules is present at room temperature, which is more higher than this minus 273 degrees Celsius. So because of this thermal energy, they would be in motion state. The motion which is called random motion. If you imagine one molecule, air molecule, it is moving straight away because with some velocity it has got because of the thermal motion. And while moving, it may hit the wall of the container and undergone reflection. This collision with the wall of this molecule, we can call it elastic, purely elastic. And it is reflected back and again going to hit with another wall. But meanwhile, it is traveling straight direction, along straight path, and again undergone collision and moving straight away and hitting to another wall. In that way, any molecule is said to be in random motion because of its energy, and it is undergoing collision successively with the walls of the container, and among themselves also they may collide. Say one molecule is going like this, another might be coming from somewhere like this, so they may collide, then they undergo reflection again. So that is what any molecule may collide with the walls, and among themselves they may collide because of this thermal energy they possess due to temperature at where room is present. And these molecules, since they are making random motion without any particular direction, they can move in any direction. And if you consider unit area in this room, imagine unit area in any orientation, these molecules, while making random motion, they may hit this unit area. So during this collision with the unit area, they may apply exact force on that area. So the total force, how much is acting on this unit area, is called pressure acting on the area, or this is the pressure of the gas. Now we are going to derive the expression for pressure of the gas by using this kinetic theory of gases. So to derive pressure of gas, first of all, imagine one molecule is moving like this with velocity v. When molecule is moving with velocity v, that velocity we can split it to three components because it is a three-dimensional motion. So into three independent directions we will have here. This is along x-axis and y-axis, and z-axis is in upward direction. So along x-axis, the component of this velocity v is, we can call vx. Along y direction, the component of velocity is vy. Along z direction, the component of velocity is vz. In that way, the velocity of the particle which is moving in any other direction, we can split as three components. Then this v bar velocity, actual velocity, can be expressed by using the components in this way: vx I cap plus vy j cap plus vz k cap. And also magnitude of the velocity will become root of vx square plus vy square plus vz square. In this way, velocity we can express in vector form by using components of velocities, and magnitude of the velocity also we can express in the terms of components. So in that way, every molecule will be having velocity components. Now let us consider particle moving in this direction because of the velocity component vx. Velocity say vx and its mass is say m. That means what? While moving, the particle will have how much momentum? mass m into velocity vx. We are observing velocity components vx only. We are living at present vy, vz. So as vx velocity component is observed, considered, then mass into that vx velocity is called momentum of the particle while moving from left to right. Suppose to any wall it is hitting, after it's colliding, and after collision it's coming back. It is moving from right to left. It was moving left to right. That time momentum was mvx. Now after colliding with the wall, it is reflected back, coming from right to left. Then the momentum will be m into vx again. But in direction, both momentum are opposite. If we call one negative, other will be positive. Then what is the change in momentum has taken place for the molecule, that particular molecule? The change in momentum is final momentum minus initial momentum. So then that will be equal to 2mvx. 2mvx. So this is the change in momentum of one single molecule because of the collision. But how many molecules are there? We have to count. To count, let us imagine in unit volume, how many molecules are there? Molecules number we can call small n. So in unit volume, if there are n molecules are present, and consider a volume whose cross section is A, and the length is Vx into delta t, because in delta t time with Vx speed it will travel how much distance? Speed into time, that is Vx into delta t. So that is what we have to imagine here. Cylindrical volume whose cross section is A and the length is Vx delta t. Then volume of this cylinder which is formed will become A cross section into length, that is Vx A into Vx delta t. This is the volume. So in unit volume, if there are number of particles are n, then in this much volume the number of particles will be into n. So these are the number of molecules which are having velocity components Vx. But all these molecules, will they move towards right? Means what? We cannot expect. Because due to symmetricity, we can imagine half molecules may be moving towards left and half are moving towards right. So that's why only half we have to take which are moving towards right and hit the wall. So if one molecule is hitting, undergoing collision, then change in momentum we calculated 2mvx. And these many number of molecules, if they hit the right side wall and undergoing collision, then change in momentum will be this number of molecules into 2mvx. This is the total change in momentum. Then 2 and 2 got cancelled. So this is the expression for change in momentum delta p. So this is the expression for change in momentum delta p. Then what is the rate of change of momentum? Delta p by delta t. This is called rate of change of momentum. This answer will be A Vx n into m Vx. That is equal to A Vx square m n. So this is the rate of change of momentum, which is called force. And if this is the force, then what about the pressure? Pressure is nothing but force by area. And force just now we calculated how much it is A Vx square m n by area is A. So then area got cancelled. Then pressure expression we got Vx square m n. So this is expression for pressure at present we got. But here one problem is coming. We imagine all the particles are having velocities Vx, but it is not correct. One particle may have velocity say Vx1. Then its velocity square is Vx1 square. Another particle will have velocity Vx2. Velocity square is this much. Like that, there are different kinds of velocities are there. So that is why if there are n velocities we consider, then nth particle's velocity component is Vxn square. Then we have to find average. Average means what? All summing the velocities, velocity components, x components of velocities, squares of the velocity components, and divide with total number. Then we get average velocity component. That let us show with Cx square. So this average velocity Cx square we have to put in the place of Vx square. Then pressure will become, on average pressure will become how much? Cx square mn. So this is the velocity. But if we consider velocity components Cy, then pressure would have Py is equal to Cy square mn. If we consider velocity component Cz, then pressure expression would have become Cz square mn. But pressure should be same in all directions, we know one point. So that is why all these three must be equal. That means Px must be equal to Py must be equal to Pz. That's why that average pressure we can call P, which is equal to sum of these three divided by Z, because these three are individually equal to each other, divided by 3. So that means what? 1 by 3 into Cx square Mn plus Cy square Mn plus Cz square Mn. So this is the, then Mn is taken common, then Mn by 3 into Cx square plus Cy square plus Cz square. Now this velocity just like here I told, whenever velocity is v and components for vx, vy, vz, then the relation for magnitude of velocity is v is equal to root of vx square plus vy square plus vz square. Here also, if velocity is c, then components are cx and cy and cz, then the relation must be c square must be equal to cx square plus cy square plus cz square. So that is why Cx square plus Cy square plus Cz square we can replace with C square. Then the pressure expression finally becomes Mn by 3 into C square. So this one. And one more point here, N is number of molecules in unit volume and M is mass of each molecule. Then M into N will become mass of unit volume. Mass of unit volume is called density. So that's why we can replace that Mn with the density rho. So then the pressure expression becomes 1 by 3 rho C square. So here the C is called the root mean square velocity of all the molecules. In this way, pressure expression we derived.